Okay, good afternoon, everyone. I am Ramaswamy, and I'll begin this presentation. First of all, I want to acknowledge the help we've got in assembling this presentation. My colleagues from GFDL, Whit Anderson, Young Cho, Paul Genu, and Gabe Vecchi. And then also many thanks go to all the people who organized this event. From the State Department, Isabel Gates and Georgia Mew, along with a host of other people you see on the side there. They are kind of responsible for really bringing this event to life. Amanda McCarty, who is not here, I think, from NOAA, who actually enabled the organization of the presentation in terms of giving very useful tips and feedbacks. And then the use of the hyperwall from NASA, Eric Sokolowski, who's here, and his colleague Leon Estrada, who actually were able to get some of the movies that we're going to show done for the hyperwall. All right, so there are only a few points I want to cover through slides. And one of them is just to depict the complexity of the Earth system. What are we trying to understand and predict? It's all these things. Changes in the sun, changes in the atmosphere, changes in the hydrologic cycle, changes in land, changes in oceans, changes in biosphere, and the way the system interacts amongst all these components to give us the climate and the extremes that we're going to talk about. So that's kind of number one factor, the complexity that you want to capture. And then let's get into the situation of what is observed. So IPCC reports bring out a lot of the science and the assessment of the science as it happens every 5 years. And I'm just picking up a couple of results from the IPCC 2013 report, Working Group 1. And basically, the central point is there's multiple lines of evidence of a warming world. There's no doubt about that. You look at the temperatures over ocean, they're rising. Temperature over land, that's rising. Temperature of the lower atmosphere, that's rising over the last 100 years. And ocean heat content is rising. Basically, oceans take up the heat that comes into that's put up in the atmosphere. Sea surface temperature is rising. Global sea level is rising because water expands. That's kind of the principal component of sea level rise. And then the flip side of some things have to decrease. The Arctic sea ice is decreasing. Snow is decreasing around the globe, and glaciers are decreasing. So all taken in togetherness, these are the signs of a warming world, not just one variable, but multiplicity of variables. And then looking further at sea level rise, an issue that Michael Oppenheimer is going to talk about in terms of risks. What you see is the satellite altimetry measurements of sea level rise everywhere, and the reds indicate a lot of sea level rise over the last, this is actually a 20-year period, 8 millimeters a year. Here this part, and then yellows in many parts. But of course, sea level rise, the one point on this plot is that sea level rise is not rising uniformly. There are some parts where it's not, for well-known reasons. And then if you look at individual stations where you have tide gauge measurements, and the red line on these plots is the global mean sea level rise. So you can see in some of the cases, the tide gauges are showing agreement, like in San Francisco, agreement with the red line, which means that sea level rise there is almost the same as the global sea level rise. But in some places, it is not. In Stockholm, actually, it's a decrease, partly because of the isostatic rebound issues. And then in some places, it's far greater locally than global mean, like in Manila. And then in some places, there's a lot of oscillations. And this is actually very representative of El Nino oscillations. And that's why this appears like this. So there's a lot of things to be said about sea level rise, but it is actually increasing, and it's bound to increase as we're going to have more and more warming. All right, so what about the future? Again, drawing upon the IPCC reports, one of the major items that came out of the IPCC 2013 is the fact that the temperature increase, if you measure from pre-industrial times, is related to the cumulative anthropogenic CO2 emissions. And that's because of the two things acting here. One is the radiative effects of CO2, but the other thing is the uptake efficiency of the Earth system in CO2. And that gives rise to the fact that as you keep increasing CO2 in a cumulative sense in the emissions, the temperature is going to increase. So this is sort of a point that is being communicated to decision makers and is an important component of management of the CO2 climate issues. Now, continued emissions of greenhouse gases are known to cause further warming. These were model projections. And what you see is continued warming of the planet. The red lines, the blue lines are simply two different RCP scenarios. RCP 8.5 is the more sort of aggressive growth of CO2. Concurrent with that, you're going to have the melting of the Arctic sea ice. And in this case, it's interesting that even the RCP 2.5 scenario, which is kind of a low CO2 emission growth, is still causing a complete vanishing of Arctic sea ice by the well into the beyond the middle of the 21st century. And then also another thing is the increased acidification of the oceans as CO2 gets more and more CO2 gets dissolved in the oceans. Now, one of the things that this presentation is going to emphasize is, of course, we have a long-term climate change, but a key question right now for society and for decision makers is, how are we getting there from today to 2100? What's going to be the situation as we go along? And that brings in the weather. So the weather to climate is now a continuum that we have to deal with. And by continuum, we mean that on the sort of short time scales, you have these severe weather like tornadoes, heat waves, storms, etc. Then you get to interannual variations and changes, such as El Nino, La Nina situations. Then you get to decadal types variability, and then a multi-decadal, which leads to actually climate. So the whole thing is a continuum, or what we call seamless, and we have to actually now deal with this phenomena. That's kind of what understanding and prediction is going to. And one of the reasons, of course, you want to do this is there is now a interrelationship between weather and climate in terms of explaining various catastrophic events. So you have floods, displacements of society, you have snowstorms, and then on the flip side, you have drying of the continental interiors and wildfires created by weather situations, as well as these are superposed on long-term climate changes. So in terms of how do we try to deal with this, the models that are being used, the global climate models we're using, have gone to higher and higher resolutions, so that in this kind of still picture, you can see the tendency to capture finer and finer aspects of the atmosphere. In this case, it's actually clouds. And this seamless model, which is kind of, you see the title, is the drive that we are all going to, where we can actually resolve this weather-climate continuum. And so that we can actually provide the information that's being asked for from a diverse number of sectors in terms of accurate, credible scientific information with characterization and quantification of uncertainties. And some of those sectors are listed here, goes from maritime, management of forests, space operations, energy, hydropower, construction, agriculture, etc. So now I'm going to sort of illustrate this weather to climate, how we are kind of thinking about it in terms of 3 short movies. And just to describe what those movies are, the first one is going to be talking about short-lived climate forcers, and in this case, I'm taking particulates, as simulated by a global model showing the continental and intercontinental dispersion of these aerosols from their source regions. And these are important for not just climate, but they're also important pollutants, so that there's a sort of a twin problem that we are trying to capture here. Then a climate change scenario from the RCP 8.5, and showing some important aspects of the global surface temperature projections, which brings into light some elements that, again, for decision making are very important. And then finally, a really state-of-the-art model to show how we can actually work with a climate model to generate the weather that's happening. And the example that is going to be shown is tropical cyclones in a global climate model. So now if we can get to the movies. So the first movie you're going to see is one of Aerosols. It runs through a whole year, the year being 2012. The model is being nudged with NCEP reanalysis winds. So large-scale winds are being given to the model. And then you're going to see the distribution of the aerosols. So the color schemes are, the blue is sea salt aerosols. The green is black carbon and organic carbon, so carbonaceous aerosols. The whitish gray is sulfate aerosols. And the brown, orange-brown is dust aerosols. And you can see what is being imprinted by the aerosols is the large-scale circulation features, the cyclonic storms, the anticyclones. And you can see very vividly in the southern hemisphere, the sort of storms rolling in across the globe. And then some very prominent features, and this is marching in time, I forgot to tell. This is the third month. It's going through March. It's going to run through the whole year. And you see, for example, the dust coming off the Sahara, the biomass burning aerosols from the southern African regions. You can see the transport of sulfate across from the northeast US, across the Atlantic. And sometimes you can see wisps coming out across from Asia of sulfate right to the west coast of the US. Then you can also see over Asia, as we approach, this is May, you can see sort of the absolute agglomeration of all kinds of aerosols, dust, sulfate, black carbon. And one thing you notice is that these are short-lived entities, but even though they're emitted in one place, they can actually travel long distances because of being carried on the backs of winds. And we're coming now into June. You again see, you can see the flow into the Arctic too. Some of the aerosols actually go well beyond the northern latitudes up into the Arctic. And so it is actually a very vivid collection of really what happens to even the short-lived tracers, because they travel long distance and therefore have the ability to affect climate in a global fashion, even though they're emitted locally. And as we come to, this is now August, as you come into October, the 10th month, you'll actually see a big dust storm from the Midwest going right across, and then right after that, Hurricane Sandy spins off into the Northeast. You'll kind of see that as we approach the next month. This is now September. And you see dust even in the sort of the deserts, the arid lands of Australia. Very realistic, actually, simulation. And in fact, this is being compared to observation. And now you see the Hurricane Sandy there spinning off into the Northeast. Now, the next segment is another aerosol movie, but this is actually now focused on East Asia. And this is running over a period in 2012. And here, this is actually white now is sulfate and carbonaceous aerosols showing a very dense pollution over that region of these aerosols. But you also see dust coming from way across Mongolia into the Asian region. Next is Australia. And this is actually a particular year, 2009, when there's actually a lot of dust which cropped up from middle of Australia. But you can see that, again, the dust and the sea salt, which is coming off these storms, the high southern latitudes, actually mixing with each other. And you see this big tongue of dust actually going across right off the southern coast of Australia. And also carbonaceous aerosols, too. I forgot to mention, the brighter the coloration, it means the more heavier the loading at that point. And then finally, so this is a really big jacket, and this is actually NASA satellite observations actually recorded this. So I'm going to wait for this to finish, and then the last part of this movie is actually showing how you can actually use these models to take source regions individually and watch the transport of dust. This is a natural dust from the surfaces in the Sahara region and going all the way across to actually South America. There's actually paleoclimatic evidence that a lot of dust in South America, a lot of dust samples in South America actually can be traced back to the flow from Africa. And you can see that as the sort of seasons change, this is now May, as seasons change, the flow sort of becomes a little bit more westward, and you can see that some parts of even Central America and even sometimes Florida actually get all these dust coming in from there, from different regions. But you can actually sort of use now these models to do these kind of fine analysis. And I forgot to mention the resolution. This 50-kilometer global model, so you can actually see these things on a very fine scale. But you also have flow from other places too, which kind of mingles in, which makes for complexity of analysis of where the individual dust is coming from at the receptor region, because there are different regions, different source regions from where it could have come. All right, then the next movie is going to be the global surface temperature projection. This is starting from about 2040. And as it goes to 2100, you can see parts warming. The red is warming. The blue is actually cooling, and so this brings up an important aspect that locally you can have variability such that you can actually get colder than the previous year. So intraannual variability, especially in southern oceans, it is pretty high. But as it goes to 2100, you can see that the land warms faster than the ocean, the northern hemisphere warms faster than the southern hemisphere, and the northern polar regions warm much faster than any other region on the globe. So just watch. Land is warming faster than the ocean. Northern hemisphere is warming faster than the southern hemisphere. And the northern polar regions, i.e. the Arctic, is warming much faster than equatorial or southern hemisphere regions. In fact, at the end of the simulation, that's about 8 degrees and more in the northern hemisphere relative to today. So it's not even pre-industrial, it's relative to today. And this is the RCP 8.5 scenario, so obviously it's a more aggressive CO2 scenario, and the RCP 2.5 just is lesser, but the contrast is really there. All right, this is the last movie where we're showing the 25-kilometer global model. So that's fine as some of the weather models today. And where the weather and what is represented here as a proxy is a total condensate in the atmosphere, so total condensed water in the form of clouds, water vapor, ice clouds, water clouds. And what you're seeing is storms spinning off, and these are in various categories. Tropical storm is green. When it reaches yellow, that's hurricane category 1 and 2, and then red is hurricane category 3, 4, and 5. And this is a particular year using the 2000s greenhouse gas emissions. And what is circled is when the storms form and are categorized according to the WMO definitions. And this movie starts in January, so most of the storms are in the southern hemisphere. And as you go to June and July and August, you'll see the storms moving up into the northern hemisphere. And this is fairly realistic because you know that this region is prone to many storms, so it's sort of this region here. And then as you go further into the year, you'll see storms spinning off here and off Africa. And so this is kind of a model that we're using it for seasonal prediction, which means that every month there's a 90-day prediction which is put out for anyone to verify. It's out in the website of NCEP. It's part of the North American Multi-Model Ensemble. So anyone can go and check it out. And it's giving fairly good results, I would say, reasonable. There's still a lot of things to be ironed out in this model, but it shows the capacity that we have today to actually go into the climate models and actually do weather in those climate models so that you have a seamless model, not only a system, but just a seamless model that goes all the way from hurricane time scales, to longer time scales, intraannual, decadal, centennial. So you see some of these storms are pretty vicious. Category 3, 4, 5 with wind speeds exceeding 60 meters per second. And it also shows sort of how the circulation is spawning these storms. Just interested to watch this quietly without my speaking. It's so spectacular. And all these regions are just, and this is a coupled model, coupled ocean atmosphere free-running model. So it is not yet a prediction model because of prediction, you want to use initial values to drive it. That's not done in this particular movie, although this model has been used to do the initial value problem, and that's kind of what leads to seasonal predictions that we put out every month for seasons. Now, some of the regions are not necessarily exactly the same as what is observed in nature, really, but that's kind of one of the things that we have to improve upon the model. Some regions have fewer storms than what is observed. Some regions have far greater storms than observed. Now, as we are approaching into April, you're going to see sort of this region gets very intensely active during the pre-monsoon phase, and then the monsoon seasons, June, July, August, will be totally covered with white. And that's kind of symptomatic of the condensed water that forms there. How am I doing on time? Look okay? Okay. And there are some months, like in this particular case, the month of May, not May, June. June turns out to be rather quiescent in this particular run. And you can actually see even how the storms or the motions carry the flow towards the poles. And that actually has important implications for how cloudiness and poleward transport of heat is being done in the atmosphere. Now you can see the storms have started moving up. You can see storms coming off, and some of these tropical storms actually then morph into extratropical storms. So not all of them, but sometimes they morph into extratropical storms. There's one more here. So there are some months where you don't have intense storms. You can see that January to April, quite a few hurricane category 3, 4, 5 storms, but April, May, not much. I'm waiting for storms to form here, which should happen in June, July. And you can see now the sort of cloud cover that comes into this region here as we go into May and June, and starting to pick up over South Asia too. And there is one. So there's a pretty quiescent time in May, June. And picking up now, you can see the monsoon picking up with the white condensate over the almost entire Asia. And now you start to pick up storms here, forming off the coast of Africa, moving westward. And there's only one which actually strikes the coast in this simulation, but you can see a lot of them coming up and then sort of veering towards the northeast and not necessarily reaching the coast. 3 minutes? Okay. There's one. More spinning up here. And more spinning up here, too. This actually, in this simulation, that turns out to be a pretty violent region in terms of storms. They keep coming up. Okay, you can see a lot of storms there off Asia. This one is the most powerful, 76 meters per second, which went up in Asia. Okay, and there is one more. I don't think it goes all the way. They keep forming in clumps here for some reason, one after the other. Okay, so you get the picture that the capability exists with a model like this to actually look at the weather in a climate change context. And I think that was the major point, that you can catch with the models now the complexity of the system, as well as provide the regional information on these tropical storms. So I think I'm going to ask the movie to shut off. Gary? Okay. So now we are, the next slide, please. Oh, sorry, I got it. So we're going to now turn to Michael Oppenheimer, who's going to talk about prospects for impacts and adaptation along the coast, and talking about climate and climate change and the risks. So Michael, over to you.
Thank you for inviting me to do this presentation, especially via video link. I won't actually be in Paris until next week. The point of my presentation is to emphasize that adaptation to the consequences of climate change is not just a theoretical concept, but rather a current necessity in the minds of decision makers in both developed countries like the US, but also developing countries. The key concept to take away from this presentation is that while much of the focus heretofore has been on emissions mitigation, and while emissions mitigation remains a top priority if dangerous levels of warming are to be averted, at the same time, climate changes are baked into the system basically until around 2035 or 2040. That is, the climate changes we're going to get over the next 25 years or so are rather insensitive to the emissions pathway we follow over that period, with emissions mitigation becoming much more important beyond. And that therefore, there are climate changes that have already happened and that will happen in the next couple of decades that will demand greater action on the adaptation front. It follows that the rather inadequate responses we often have to current levels of climate risk should be a grave concern, because over time, as I said, the risk is going to be increasing, and it's going to be increasing continuously. For instance, according to the fifth assessment of IPCC, the days which are historically the 10% hottest over the previous many decades are going to occur about 30% of the time by the year 2035 or 2040. A coastal flood level, which was reached only about once every 100 years, the so-called 100-year flood, could occur by the end of this century every 10 years, every 5 years, according to estimates in the fifth assessment. So the physical side, the probability of events which are difficult to adapt to already are going to be increasing. What I'd like to emphasize now is the interactions of humans and the climate system, which is shown in the next slide. This propeller diagram from originally the so-called SREX report, but also it's in the fifth assessment. A sensible objective of policy is to decrease risk. Risk is made up of three components: the probability of occurrence of a given level of damages, like a flood or a heat wave. That's the physical side. That's the side that on the left that can be affected by emissions mitigation. But then we have two components on the right, which are really on the socioeconomic effects. Those are vulnerability and exposure, and they can be managed through improving efforts at adaptation. Exposure means people, infrastructure, ecosystems basically being in the wrong place at the wrong time and exposed to extreme climate events. Vulnerability means the sensitivity. If one is exposed to such events, what's the predisposition to harm or damage? And so again, adaptation means reducing, through adaptation, both vulnerability and exposure. Now, I'm going to emphasize coastal risk arising mostly from sea level rise and potentially from intensification of, for instance, tropical cyclones or on the US coast, hurricanes. Let's see the next slide. This slide illustrates that exposure, which is one of the important components of risk, is made up not just of the extra amount of exposure due to climate change, that is, for instance, warming leading to sea level rise and causing floods to penetrate over greater areas along the coast, but also that changes that are already happening and which may become more intense in the future. For instance, changes in the amount of in the numbers of population along the coast, which on this slide, for instance, let's look at the furthest left-hand bar, which represents the change in exposure to the current 100-year flooding by 2070. You'll see that the current exposed population, and this is in thousands, so for instance, the number in the lowest side of the left-hand bar is equivalent to a population of 5 million. The light green is today's exposed population. The dark green is the added population by 2070 that's exposed just by socioeconomic changes, and that means more people moving into the coast, for instance, more buildings, etc. And the yellow ball top is
Hello, bear with us for a sec to see if we can get back the audio or tell Dr. Oppenheimer that we can't hear him. The joys of technology.
Am I back? Okay. Let's look at the next slide. The third slide refers specifically to coastal risk around New York City, and it draws on and I use it because I live in New York City and because it was a subject of particular damage in Hurricane Sandy in 2012. So the third slide makes this point about vulnerability and exposure in a different way. And it shows both our lack of being prepared, but also how much the risk can change due to relatively small sea level rise amounts in the future. So a key benchmark for resilience of the city is the continued function of the subway system, which is the lifeblood of New York. During Sandy, the system was knocked out for 3 or 4 days. A combination of very dedicated transit workers and a lot of good luck allowed the seawater, which is very corrosive, to be pumped out of the system quickly and thereby save the system from potentially months or more of shutdown. Now look at this figure, which shows the top flood levels in all coastal storms, the 10 biggest ones over the last 65 years. The storm on the right is Hurricane Sandy. You'll note that the flood level was way above, it's 14 feet above low tide, way above all the others. But notice also the horizontal red line. That's the flood level at which salt water gets into the subway system and potentially corrodes it. So here are the two messages from this slide. Number one, if you added a foot or two of sea level rise, which is the projection, by the way, for New York City by mid-century, you would have moved almost all of those storms up above the 10.5-foot line, which means they would have flooded the subway system. The other lesson is that despite this experience of almost flooding the subway system 9 times before Hurricane Sandy, almost nothing was done to protect the system. And that's kind of indicative of how difficult it's been for policymakers to move forward and address the current level of risk without even thinking about what the increased risk is in the future when a storm like Hurricane Sandy, instead of occurring maybe every 500 years, by the end of the century occurs maybe every 10 to 50 years, according to the projections we have. The story is somewhat more promising for heat waves, where the ability of local governments to act to protect against a risk has improved over time. But overall, our ability to respond, the record on responding to extreme climate events is not particularly promising in face of the increasing risk. In the meantime, we're really in a position of having to make decisions which are important for whether we should do the relatively straightforward things like moving emergency equipment for hospitals and other buildings out of the flood zone, plugging subway entrances, etc., or doing large-scale expensive projects like building surge barriers like the one on the Thames. And frankly, we are not really focused very well on what's needed to happen to actually make those decisions. So let's see the final slide. And here I just want to make the point that even relatively simple measures, doing the simple, straightforward things that would be necessary to cut today's risk, can have an important effect in reducing the increasing threat in the future. So consider what would be possible if we just implemented current best practices. I just give you the example from Bangladesh, because it's a poor country. There are 150 million people in an area the space of Wisconsin, and it's been victimized by cyclones for eons as they come up and hit the south coast. on the north end of the Bay of Bengal. In 1970, about 1 million people died in a cyclone that hit the coast. Today, similar storms bring much lower death rates. Still not good, but in the thousands instead of the 100,000s. Why? Because the government helped get together an early warning system to let people know storms were coming, and build concrete bunkers like the one you see on the slide here to give them some place to go. The lesson is straightforward. We ought to start doing a better job in dealing with today's risks, even doing the relatively simple, straightforward things that sometimes we don't do, in order to smooth the path to improvement in adapting, as inevitably the probability of heretofore unusual events like Hurricane Sandy inevitably increase over the next few decades. Thank you.
Hello, is this working? I'm Barry Edmore, and I'm delighted to be here. I'm going to be talking about atmospheric carbon, particularly atmospheric carbon dioxide and methane. And as Ram showed, there's a very strong relationship between atmospheric carbon, particularly CO2, total emissions, and temperature. So what is this carbon cul-de-sac? And I'm also going to be addressing something that Michael Bloomberg has said. If you can't measure it, you can't manage it. So what we need is a carbon observing system that would be based in terms of in situ measurements on towers, ships, and aircraft, as well as satellites. Right now, we have 2 satellites that are devoted to measuring greenhouse gases, the Japanese Global Greenhouse Observing Satellite, GOSAT, and the Orbiting Carbon Observatory, OCO2, by NASA. So we can say that we have a sparse, exploratory, carbon observing system, framework that is, but what we need is a dense, robust, sustained carbon observing system. And I want to just show 2 elements of that system that we need in the future. First, the 2 satellites that I mentioned, GOSAT and OCO, the Orbiting Carbon Observatory, are in low Earth orbit. That is, they orbit from pole to pole, and then as the Earth turns, they trace out fractions of the atmosphere going from pole to pole. That's very useful. We have weather satellites that do the same thing. We also have weather satellites that sit in geostationary orbit and stare at the Earth. And I want to talk about one such initiative that we need in the future. I won't dwell on this, but it basically shows a 4-channel spectrometer. This is exactly like what the Orbiting Carbon Observatory looks like, except it has an additional channel to measure methane and carbon monoxide. And it would be in geostationary orbit, and this is just 3 examples, and it would be able to measure wall to wall, multiple times a day, each of those rectangles, so that you would actually now begin to map regions of the world. This gives you an example of that in the Shanghai-Nanjing area. The geostationary satellite is essentially mapping across this grid every 3 kilometers by every 3 kilometers, multiple times a day, looking at all of Southeast Asia. Whereas in this particular area, the Nanjing-Shanghai, the little green bands show the Orbiting Carbon Observatory going by on day 1. 8 days later is the next time the Orbiting Carbon Observatory would visit this area, comes in and out to the east. 8 days later, 16 days, it repeats the original track. Whereas from geostationary, you could be mapping every day, multiple times a day, this entire region, in fact, all of Southeast Asia. So that would be a new element that is needed in a carbon climate observing system. Let me show you an additional element. And this builds upon what Phil DeCola talked about earlier this morning when he was looking at cities. In fact, the most logical city to look at is Paris. We have right now 2 lasers, one at the University of Paris Science in Jussieu, on the tall tower and one just in front of Montparnasse on a tall tower, but not as tall as Montparnasse. So these are two lasers, and they send out a signal on the absorption band of CO2. And they hit a reflector, and the signal comes back. You measure a change in the strength of that signal. And from that, you can infer what the carbon dioxide concentration. This gives you an example of what you can see every 5 seconds. So the blue are the two laser the laser sending signals. The little circle around the peripherique, those are the reflectors where you can see the signal coming back. So you can see the one in the, more or less in the center of the picture, that's just in front of Mount Montparnasse, and the one over at Jussieu, where it says T1, Jussieu Tower, that's the one at the Science University. So each of these is sending out pulses, and with that, you can measure the carbon dioxide concentration every 5 seconds. So, as I said, what you can't measure, you can't manage. Clearly, we're going to have to manage the carbon question. This is not a problem that is going to go away. And so what I've tried to do is introduce very briefly 2 elements of a future carbon observing system. Thank you very much.
Thank you for that. We do have plenty of time for some questions and answers with our guests. So with that, I will remind everyone watching on the live stream, feel free to ask questions using the hashtag AskUSCenter. But with that, I'll take any questions from the audience. All right. Well, I'll start off then. I have a question for all of you. I guess you can probably all touch on this a little bit. It seems like what we're talking about a lot is we saw the modeling techniques. We saw this idea of vulnerability and risk and that sort of communication and this carbon observing system. In what sense, how do we communicate this? How do we communicate what we're seeing from the models? How do we communicate what the models say about vulnerability to the policymakers? Because you're the scientists. How do we communicate what you're seeing so that they'll understand what they could possibly do?
So I'll take a stab at it, and then Michael and Barian can add to it. Speaking from the modeling side, I think one of the ways in which communications is going on currently in the present times is through the IPCC assessments, particularly the science coming through from Working Group 1. And I think that does a lot, but there's probably more room for improvements, particularly in terms of the characterization of the uncertainties. You know, what are the uncertainties, and how are we going to not just specify the uncertainties, but how are we going to get over them? You know, whether it's uncertainties due to short-lived forcings like aerosols and ozone, or whether it's uncertainties due to clouds, or whether it's uncertainties due to carbon uptake, or whether it's due to heat uptake in southern oceans. All these are leading uncertainties in terms of how global warming is going to proceed. But we have to do a better job at communicating the science part, and I think IPCC process demonstrates how it can be done, but probably I think more should be done in terms of actually a more concerted strategy to be communicating not just in the 5-year IPCC timescales, but really all the time. I'll now pass on to, let's see, I'll go Michael, since Michael was next. Michael, you want to add something to that?
Yeah, sure. I just want to pick up on that comment by saying that I think what's important as we move into a phase where local decision makers are very concerned about adaptation planning, that some of the basic science, which develops ways of communicating, scientists communicate uncertainty and their sort of best estimates in a particular way, but developing interactions with stakeholders who actually have to make the decisions from an early phase is going to be critically important. For instance, I'm on a panel called the New York Panel on Climate Change that provides technical estimates to the mayor's office. It was put together by Mayor Bloomberg originally and carried on now by Mayor de Blasio. And we are from the beginning not just developing estimates of flood risk, but getting together with stakeholders to see what they understand and what are the numbers and the framing of those numbers that they like. There's a tradition in the scientific community, partly because of the requirements of the insurance framework we have in the U.S. to frame things in terms of the once in 100-year flood, but is that the best way to talk about it, especially in a situation where the risk is changing, the probabilities are changing, and the uncertainties are changing too? So my one recommendation would be that the process of engagement with stakeholders has to start early and be carried out often.
This is Barry and Moore. I'd like to build on what Michael just said, and particularly focus on two stakeholders, the mayors of cities of the world. I think they understand it. They're at ground zero. They know that they need to do something. Action is not out of their framework. And secondly, the major businesses of the world, the reinsurance companies, the technology companies, the transportation companies, they understand this, they get it. So I think that by focusing on decision makers that really are at ground zero, that will be a very important part of the communication process.
Thanks.
Thank you. Ram, can you say something about the utility of the high-resolution model that you showed, where you could conceive of doing a ensemble run with a certain scenario and then develop PDFs of extreme weather at some point in the future? Is that something that's possible with that capability?
Yes, it certainly is. I think that, in fact, the procedure you outlined is exactly what we have in mind. And in fact, it's even in process in terms of seasonal prediction. But in terms of, let's say, decadal, multi-decadal predictions, yes, that's kind of the process that we think is no longer a dream, no longer an act of fiction. It's actually possible. And then actually, once we have this thing going, the main process will be one of verification, because that's when you build confidence in the models. So hopefully, I mean, the experience generally has been that as you go to higher resolution, you're capturing more regional information, but it's not only that. You're solving the equations on a much more finer scale and leaving less to, let's say, formulations that are cooked up. They're actually more ab initio. So because of that, you actually get improvements both on the physical science side and then on the interpretive side, because you're capturing regional information much better. But I don't want to minimize the issue of complexity, which I didn't elaborate on much. But as you go towards, for example, constructing PDFs, I think it's going to be important to test what complexity is getting you. And sometimes it can get you garbage. So you have to be aware of that. But hopefully, some kind of a rational pathway would actually see complexity absorbed in the model actually going and doing better things in terms of model simulations.
Ram, real quick, can you just describe the benefits? This is me over here, sorry. Can you describe the benefits of PDFs, just so folks who may not understand what those are?
Okay, so PDFs are probability density functions, probability distribution functions. And basically, when you're starting to predict the weather, or you want to know, starting from today, what is the condition going to be 1 year, 2 years, 10 years, 20 years from now, there are certain, there's of course, let's say there is a climate forcing going on by CO2. But on top of that, you also have what is called the initial value problem, where depending on the state today, under the same forces, the climate can evolve along different trajectories. So how do you cover the ground according to different trajectories? Because sometimes the initial state is not well known. For example, we don't sample all parts of the atmosphere, and we don't sample all parts of the global oceans. So how do we start to get about an initial state of this Earth system becomes a big problem in itself. So what happens, and this happens, for example, in the weather forecast models, there are several ensembles run where you start from different initial conditions, slightly different from each other, to see where the system wants to go. Now, it would turn out that most of the, for weather 24-hour, 48-hour weather forecast, most of the tendency is toward a certain direction, but you only know about it after running several members of the so-called ensemble. Typically, I think in the US weather forecast, something like 80 to 100 members are run. So you take the average of those, that gets you a mean weather. So similarly to that, we want to extend the same principle to the climate system, which goes back to Phil's question of the PDFs, that you want to be able to run several ensemble members so that you're sort of not only looking at the mean, but you're also looking at the possibility of extremes. Because the Earth system goes through a simulation only once. If you're watching the weather between today and tomorrow, that's only one realization that the Earth system is going through. Now, numerically, and because we are smart human beings, we can actually construct several different states. But ahead of time, you have to sort of guess, or you have to make some educated rationale as to which one is going to be the real track of the system. And that's what you don't know. And that's where the number of members, number of ensemble members that you have begins to dictate how accurate you get to the end. Even then, there are uncertainties. But it's one way of getting into the uncertainties, and that's kind of what is meant by the PDFs, doing several calculations, starting from different initial conditions.
This is a brief question for Barian. Barian, I think the geostationary carbon sensor is an extraordinarily important idea. But my question is, what is the maturity and prospects? Is it a technology that we understand well, that we can get this kind of a satellite up in the relative near term of a few years? How far are we along in reaching this, I think, very important goal?
Well, from my perspective, like three. It's not turning on.
From my perspective, I think that we can do this today. And the reason being is that the instrument is essentially what is flying right now in low Earth orbit, the Orbiting Carbon Observatory 2 from NASA. And all we've done is just add an additional channel to measure methane and CO. And you get your signal to noise, that is, I can get the accuracy I need, even though I'm much further away from the Earth in geostationary orbit, by staring. So I stare for 4 seconds, and that gets me the signal to noise that a low Earth orbiting satellite has. And then I look slightly to the west, a stare, another 4 seconds, look slightly to the west, and map out those rectangles. So essentially, it's the same technology we have on orbit right now. And certainly we know how to build geostationary satellites. In fact, the Earth launches a geostationary satellite about once a month for communication purposes. The bottom of those satellites is essentially empty. So you've already got a potential host right there. So I don't see any limiter in terms of doing this.
Yeah, thank you. I'm Keith Shepherd from World Agroforestry Centre, Nairobi, Kenya. You've made a call for collecting a lot more data, daily data, higher resolution data. But have you actually gone back and identified the decisions that you hope to support with this data, formally analyzed them and calculated the value of information? Because time and time again, it's been shown that we're collecting the data in the wrong places to actually improve decision making. So I'm asking, have you actually gone back and looked at the decisions you're trying to inform and formally analyzed them to identify the critical data needs?
So let me try to understand your question. Is a question about the decisions being made on the high-resolution data, and have you gone back and revisited them?
No, the users. Who's going to use this data to make which decisions?
Use the high-resolution data.
Yeah, the data you're collecting. Yeah.
It's you know, it's I would say it's a work in process. I don't think we have really gone back and used all of the high-resolution data to analyze kind of what happens when you use or don't use the data. Are you talking about atmospheric data or oceanic data? What kind of data are you talking about?
Several of the speakers have made a plea for collecting a lot more data, and that's the priority, is to collect more data. I'm challenging you as, you know, do you have a really clear understanding of the decisions that people are actually making with all this data? And have you formally analyzed them to see where is actually the value of information in those decisions? I mean, what is the critical data actually needed? I mean, is it the data you're collecting, or could it be some other aspect of data? Yeah.
So I can think of, you know, I can think of two contexts to the best I can think of right now. One is in the ocean context. There certainly has been a lot of work in using models in trying to piece together what additional information you'll gain about the climate system by actually getting a much more denser network of surface ocean data as well as subsurface ocean data. And with regards to the subsurface ocean data, I think there's been an absolute revelation in the information that that is providing for improving weather forecasts. And by weather, I think I have to go all the way to actually seasonal. The seasonal forecasts seem to improve tremendously, starting from about weekly timescales when you ingest the subsurface ocean data. And that actually was shown, the value of that was shown by models first, and then the Argo floats are now starting to go deeper. These are the measurement components. And those instruments are going deeper and collecting data, and actually now it is well known, it's well understood that you get better information. You know, on the atmosphere side, certainly we haven't sort of done that much, but I think the looking at, for example, the NASA GEOS assimilation systems, as well as NCEP's work, you have to say that there have been some cases where the data has come before the realization as to what the value of that has been. So it's been a little bit backwards. And I think there's an emphasis now on actually doing these so-called Aussies, observing system simulation experiments with models, with high-resolution models, to actually figure out maybe more intelligently where you can collect the atmospheric data in a manner that is going to befit and improve the weather simulations. So I'm not sure I got your question exactly. I'll maybe defer to Barry and if he wants to add something to this.
I think two aspects. One, certainly with the advent of satellites, weather forecasting has improved. I think that's very clear. However, I think Michael Oppenheimer showed that we may make improvements on, shall we say, the scientific end of things. And that does not necessarily always translate into people making better decisions. I'm from the state of Oklahoma now, and we're very concerned about severe weather, particularly tornadic conditions. And we've seen an actually doubling of warning times, but we've not cut the death rates because people don't necessarily do the wisest of things with increased warning. Hopefully on the climate question, we will learn from that mistake.
Yes, I'm Mr. C. Ahmed. I'm a former UN director dealing with Montreal Protocol, protecting the ozone layer. And I'm a climatologist, and talking about uncertainties, was just wondering, when we're talking about climate change and how many of the parameters are really interrelated to climate. And when we talk about climatology, we know that many of the parameters are very important for climate, like, you know, deforestation, like loss of biodiversity, like growth of population, industrial pollution, El Nino, El Niña, Gulf Stream, et cetera, et cetera. So I was wondering, to what extent do we add up all those parameters to build up those models? And I'm always a bit, let's say, worried when it comes to modeling, because we all know then, especially when it's on a long-term, let's say, basis, whenever we have uncertainty, it can really, really get you to very different results. And my question would be, don't you think that just focusing most of the time on just greenhouse gas emission is not a shortcut to explain the change of our climate? We definitely believe that climate is changing because of human activities, but all human activities. And why don't we come back to the spirit of Rio in 1992, when we were trying to tackle all the issues related to our climate, related to our, let's say, planet as well, whereby all the problems that have been being caused by human activities are all put together. So I'm just wondering that whether a conference like this one should not also talk about all the problems that human activities are bringing about, but rather than just to focus on emission of greenhouse gases. Thank you.
Michael, you want to take a first stab at that question?
In every place, more and more is the buildup of the greenhouse gases. Now, it's certainly true that each individual location, each country, each region on Earth has other problems as well, which are related to environmental change, and we certainly need to deal with all of it eventually. But we need a special focus on greenhouse gases because A, it is the one problem that's global, and B, there are things that can be done about it and should be done about it starting immediately. That's not to slight the other aspects of the global environmental problematique. But if we don't do the greenhouse gas problem, the other stuff will never solve the other problems either.
I would add that it is the modeling exercises by all the models in the world almost. They take into account the various gases, the famous greenhouse gases like CO2 and methane, but also nitrous oxide and all the halocarbons, including going up to sulfur hexafluoride. They're all taken into account. And the attribution calculations, where you start attributing the given change in, let's say, the model simulation to different elements, different entities, shows that most of the major effect is due to carbon dioxide in the sort of model-induced global warming run. In the global mean, it is certainly true that when you start to get to regional levels, there may be other contributors which are just as important. For example, aerosols in certain regions, which are very, very, over Asia, for example, aerosols do play a large part in terms of attribution. But in terms of just the global mean, CO2, the focus gets there because it is, of all the gases we know, it has the longest residence time. So any molecule of CO2 being put out today, you just know from all the known physical and chemical principles, it's going to be there for a long period of time. Methane, nitrous oxide also are there for long periods of time, but less so. Halocarbons would have been there for an even longer time. And in fact, if they had not been phased out, they actually would have, if you go back to calculations in the 1980s, they show that if halocarbons had been increasing at the rate they would have rivaled CO2 as a major contributor by 2030. But because they've been phased out, there's kind of one sort of less thing to worry about. But certainly, I think on the local scales, we still worry about the short-lived species, aerosols. In polar regions, we still worry about ozone. Stratospheric ozone depletion in the Antarctic still affects climate in a way that is not direct. Indirectly, it affects the Antarctic climate, surface climate, and therefore it can affect then kind of circulation throughout the southern hemisphere. In the Arctic, when you have ozone depletions during certain winters, that does affect the Arctic surface climate. So we worry about them in the context of regional surface climate. That's certainly correct. But the global mean, CO2 is the major problem, but not the only one, certainly.
All right, thank you. Can we give the speakers another round of applause?
Thank you.
And thanks for great visualizations. So that concludes this event.